Welcome back to another HVAC-Engineering-Techie training video. These training videos are technical in nature and intended to help your career. Remember, this is the channel that talks all things HVAC, engineering design, construction, equipment systems, test and balance, controls, efficiency, and performance. Today's lesson is HVAC technical commissioning, point-to-point testing. This is actually the most important part of commissioning, of technical commissioning. So this will be an interesting session today. Before we start, I'd like to ask you a big favor. If you become a subscribing member, if you haven't already, just hit that like button down below. Give me a thumbs up if you like the videos. I really appreciate it. It's absolutely free to you, cost you nothing. It's painless for you, but it's really important to me because Google uses that data to evaluate these videos, which keeps me on the air. So I'd really appreciate that. Would really help me out. All right, let's get started on how you actually do point-to-point tests and how the forms look like and how you actually use them. This is an important video. Thank you. So today we're looking at how do you actually do a point-to-point test on a control system. We get right down to the nitty-gritty details. We kind of reviewed this at a high level during the PFT check sheet session, Cx-4. But now let's look at what's the difference in control point testing. Process commissioning believes control point testing is a part of the control contractor startup activities and does not require commissioning field activity. Technical commissioning experience of doing commissioning point-to-point tests has proved this is a very necessary commissioning activity. It is critical to the providing the control system is installed and working correctly. To fail to do this result in many failed functional tests due to out of calibration sensors or poorly functional actuators or devices. It's really important. And when you're doing a maintenance on a system, you do a point-to-point anyway. So I don't understand why people would not do this. It's extremely beneficial. It's a great teaching tool, and it actually makes the system work. Now, control contractors, I can talk about control contractors because I was one for many, many years. Control contractors are really good at proving their first programmed controller works perfectly, but not so good at verifying the additional controllers that are downloaded from the prototype are also working correctly. They also very seldom check their sensor calibrations and almost never use a calibrated instruments if they do check them. So the calibration, I guarantee you, will be a problem, and you'll need to check that. So this is the test we do. What are point tests? To verify the control system points are installed as specified. To verify all points have the correct polarity, meaning they open when they open and close when they close, and are working correctly per the design. To verify that all input components are properly calibrated. To verify that all output devices are ranged correctly. It's part of the process we need to do. To verify control points are correctly indicated on the graphic screen as required. This is why we do it from the graphic screen to the field eyes. No matter how many interactions it goes in the field, that's the 2 points we want to make sure they're the same. To verify the system is ready for functional testing. All right, preparing for the point test. What do you have to do? How to prepare. Verify the control system is ready for the point testing. The controller installation is complete. All controller startup is complete. Controller programming is complete. Graphic programming is complete enough to allow point manipulation and status verification from the screen. Verify control contractors have completed their loop checks for loop polarity, operability, and that the loop connects the correct device to the correct design point. One of the things you got to watch out for is in the control world, it's possible a lot of times that they have canned sequences or canned graphic plates, and all you have to do is change the device name and it changes all the points automatically. Or sometimes you have to do that mechanically, so it's something you have to check, because if that points were not brought over correctly or were manually input and input wrong, what is supply sensor on fan coil 1 may not be the supply sensor on fan coil 2. You have to check those out to make sure they're correct. There's a lot of things you can find when you do point testing. Obtain all required control drawings and point lists. You need to have that. Verify that you have the required tools. Laptop with software to communicate with the controllers. Temperature, handheld calibrated instrument. Pressure, handheld calibrated gauge or instrument. Humidity, handheld calibrated instrument. CO2, handheld calibrated instrument. Electrical meter, true RMS volt and amps. Then you have those tools. They're calibrated. They're your tools. So here's how you do it. One technician in the field verifies system reaction or status. Okay, so you got someone in the field with an instrument, one technician at the graphics station operating each point or verifying status at each point. So here they are. Here's the two guys. You got a guy in the field with a calibrated instrument, and he's in communication normally. Use walkie-talkies for this. And we'll talk about, and the guy in the office is looking at the screen. Now, it is possible to have this guy be a control technician, but if that's the case, you have to be kind of clever here, because you have to ask him, in other words, it's not that you don't trust him, but you don't, right? So you got to be careful. It's best to have these two be your people, or this an operator. That works fine. Someone you know it has no vested interest to tell you it's wrong. And another thing for these systems, we normally have a control contractor there to help us with the system, but we have our people or an operator help us do this, because you're going to say, all right, I show 75 degrees at the wall sensor. And the operator will tell you, well, I show 79 degrees on that wall sensor. So we know we got a difference of 4 degrees. And so that's a little much, and we'll talk about what we do with that later on. The other thing you have to be aware of is a lot of times with the control contractor being there, you say, oh, that's wrong. Well, let me just take a few minutes and I'll fix it. You have to decide whether you're going to allow that or not. It's not that you don't want him to fix it. You'd love to have him fix it, gets it out of your hair. You don't have to make an issue log of it, and lots of stuff like that. But what happens is if he does that 20 times during the day and it takes him 10 minutes of time, you just wasted a whole bunch of hours. So normally we have them not fix it while we're there. Now, if it's a simple adjustment like, oh, well, that refresh point hasn't come in, let me refresh the computer, get that done, that's fine. But trying to change a graphic plate at that point is probably too time consuming. And if the point doesn't actually work, we don't want to fix anything in the field because we don't have time for that. Later on, one control technician to assist the operators if required. Binary digital point commands the point and field verify action and verify status is correct. Like, so the guy in the field says, okay, go ahead and start the unit. The guy starts it on the computer and it starts up. Okay, right unit started up. I mean, I've done it many times. I start the unit, nothing happens. I say, well, nothing happened. Well, the unit over there started up, so we know that this unit is not that unit, so they got the units crossed up, so we'll do that. Analog sensors using calibrated instrument, measure the instrument variable, and compare to it is shown on the diagram. Now also back up here for binary points, since most systems have status on the computer, so we'll ask the guy to start that machine up. He starts it up. Then we'll ask him to verify the status is running. And if it is, then you've checked 2 points. You started the start-stop point and you've checked the status point. So that you do. For an analog sensor, you do what we just said about. You use a calibrated instrument, measure instrument variable, and compare it to what's shown on the graphic screen. Now we talk about we do actuators. Command the actuator and field verify its position and reaction, and verify status on the graphic screen. Same thing. So if you got an analog valve, you say, well, run that valve full open, and you can watch it. Now they don't do it instantly, so it takes some time to run up there, and then you say, well, what does it show on the screen? It says 100% open. Okay, great, we're in good shape. Now, you do that, testing those both points, and these are all the easy points to do, right? So we do that. For all input sensors, compare the measured variables from a calibrated field instrument to what is shown on the graphic screen. Input and offset if the difference is twice the accuracy of the sensor. So if you have a sensor that's a plus or minus 1 degree, and your sensor is 2 degrees off, you may or may not put an offset in the system. And the reason is because if the sensor can be plus or minus 1, it can be within the 2 degree range. So maybe there's no reason to do that because you have 2 degrees on the screen. And it depends on what point that is. If it's a general point, not really important, I wouldn't do that. If it's really, really important, maybe you would do it. So there is that condition. Now here's a condition. So your field measurement was 72 degrees and the graphic point showed 78 degrees. So you subtract the two and the variance is a -6. Okay. The sign is really, really important because if you get the sign wrong, that's twice out of calibration. So, and this now there's many controllers and many kind of programming. There's line programming, which is like a basic program. There's ladder logic programming, and there's block programming. Block programming is the most familiar one nowadays. And what happens is you have an input block, and you have a logic block, and you have an output block, and this is a loop, and it's doing something. It's all within the controller, right? Well, to do an offset, see, like this is the sensor coming in at 72 degrees, and then this goes 78 degrees throughout the device, so it outputs 78 degrees. So what we want to do is we want to change this to match the 72. So we put an offset of minus 6 degrees, and we want it to go right there at the input block. Now, some systems actually let you do exactly what I've shown here. You have a little window you put there, and you put your value in here, which would be minus 6. And whenever that comes out of the system, it goes 72. Well, it comes out at 72, 72, because it's now got that minus 6 degrees. Now, you can put this other places, like I've seen them put it here or here. And you don't want to do that because this logic block may have sending that data to other functions. So it may take this 72 degrees and send it to other functions, or 75 degrees, 78 degrees and send it to other functions. So those functions won't work correctly. So we want to always modify just the input block. Now that brings up another subject is not all programmers are created equal. And I've done jobs where on day one we was there, and I was asking the technician to do me an offset, and he said, no problem, what do you need? And he did it fine. The next day, it was a different technician because the other one was busy, and I said, I need to do an offset. He said, our system, we can't do offsets. I said, pardon? Oh, no, we can't do offsets. Yes, you can. Oh, no. I said, the guy yesterday did one, and I got those blank stares in the headlights because the problem was he did not know how to do an offset. And so you have that knowledge problem that can be a problem, but they're expected to know how to do this. So that's how an offset is done in a system. For all input valves and dampers, verify that the actuators are properly arranged in either software or hardware. Adjustments that allow the actuator to go from full close to full open. For VAV terminal unit calibrations, refer to tab training modules for tab or VAV air handler systems. The tab technician will measure the current flow through the VAV box at its maximum damper position and compare it to the graphic screen amount. If not the same, they will input a calibration factor so the velocitrol will be properly calibrated so both read the same flow. That's important. And of course, our tab training T15 shows how to actually do that. So I said, also back up to number 2, when you're ranging an actuator, it's really important everything goes full closed. It's not actually required they go 100% open. That's not a problem, but actually 100% closed is really important. So what you do is you adjust the linkage on the valve or the damper to actually make sure they go closed. Digital point inputs, status point switches. Activate or override the point from the graphic screen or from the field and view results on the graphic screen. Status pressure switches should be generally verified unless used for control sequences or critical alarm, then they need to be calibrated. So let's say you got an air handler and it's got a filter pressure switch and it's got another pressure status point on the supply duct, and to tell you the truth, those probably don't need to be calibrated. If they're off 10 or 15%, it probably makes no difference. But if you're actually doing pressure control of a system, that one you need to calibrate. So you need to be smart about what you're doing. And when we come to digital points, you can override those several ways. One, on the computer screen, you can turn it on, turn it off. You can override its status on the screen to see what happens. Or you can actually do it in the field. You can go up to a disconnect switch and turn the pump off, and it should notify the screen that it's off now. And we do that in failure testing. So if you want to see if the pump rotates, you turn it off on the field of the disconnect. That's a failure, and do it that way. Digital point outputs, relays, 2-position dampers or valves. Command the point from the graphic screen, observe the device reaction in the field and on the graphic screen. If a status point is required by the design, sometimes they're not, for change in position and correct polarity. Control actuators modulating in 2-position. Command the position from the graphic screen and observe the device reaction for change in position and correct polarity. Verify fully closed position. Now sometimes if you have really slow actuators like VAV boxes, VAV boxes are dumb slow, man. They drive you crazy. They could be 180 seconds. So you're standing around trying to wait for the thing. So in those conditions, we normally do these tests for a whole group of boxes at a time. So basically we'll say, okay, we got 5 boxes in this room, drive all the dampers full open. And then as they're doing that, we're actually now on the one of them, and we say, okay, let's look at the hot water valve. Turn the hot water valve on. And a much quicker sequence, that's maybe 10, 15 seconds, so we'll get that done. And what happens is we're continuing to work while we're waiting for those stupid dampers to open, which can take forever. The reason it takes so long at a VAV box is they normally do a few rotations and stop, check where they're at, what's going on, check the sensor, and then go do a few more rotations. So they don't just do it in one full swoop like you think they were. They take a long time, so we'll do that. 100% open on an OBD damper, parallel blade damper. From 90% on, they don't do anything, it's 0. So it doesn't matter if they don't go full open, but it does matter that they go full closed. Control sensors, analog. Using a calibrated instrument, measure the instrument variable in the field and compare it to what is shown on the graphic screen. In this case, temperature, air probe. Use a stainless steel probe 6-inch or a bead sensor. A water probe could be a stainless steel 6-inch probe or an 8-inch probe. And for water, you put it in the well. You remove the sensor and put it in the well to test it. Humidity meter, or if you're doing water, you have to have a well somewhere to get it. Humidity meter, 10 to 90% range. CO2 meter, normally 350 to 5,000 range. Flow meter, whatever the range of the areas of the water. Pressure meter in inches of water column, low range, PSI, high range. So you need calibrated instruments for these different situations, and this is what you use to actually look at those points. Sensor calibration again, read the measured variable in the field using a calibrated meter and compare it to the graphic reading. If the difference offset is more than twice the accuracy range of the sensor, program an offset into the controller to make the sensor more accurate at its normal measurement range. So we're trying to get this. So in other words, if you have an instrument like a wall sensor goes from 55 to 85, that's its range. Well, you want it working really good at 75. You want it to be very low accuracy at 75. I mean, high accuracy. You want 75.1, 74.9, something like that would be really great. Be sure to observe the sign of the offset. It is very important to enter the correct sign when inputting the offset. If the difference is more than 10 times the accuracy, the sensor should be replaced because it's too much. It's way out of range to do that. Now, a lot of contractors will tell you, well, the temperature sensors are factory calibrated. We don't need to calibrate them. It depends on the type of sensor it is. If it's a thermistor or a Balco or something like that, they're actually a resistive device. So the wire actually affects the temperature range. So you have to field calibrate them. It's not that the sensor's bad, it's just that we have to calibrate it what it actually sees in the field. And if it's got 150 foot of wire on it, 50 foot of wire on it, it'll read differently, so you need that. And 10 times accuracy is pretty safe, that it's, if it's a plus minus 1 is 2 degrees, so if it's off by 20 degrees, you need to check what's going on here. That's pretty bad. If it's off by 40 degrees, now thermistors are pretty good because thermistors are the cheapest ones, little bitty ones. They don't go off by a few degrees. They go off, if it says 1,000 degrees, it's got a problem. You need to change it out because they go really large. So here's the field measurement again. The formula is the field measurement minus the graphic point, and that's how you get the sign. So if you read it in the field, it's 88 degrees, 89 degrees, and in the screen it's 82 degrees, then it has an offset of +7, okay? If you read 72 in the field and a 76 in the office, it's a -4 degrees. So the sign's really important. Don't mess that up. And one easy way to note that is you're trying to put in the machine how you will change the signal to make the screen correct. You're always sitting in front of the screen. That's the correction you want to make, not out of the device. The device is correct the way it is. We're not changing the device. We're just changing what the computer sees, and that's what we're doing as an offset. Actuator ranging. Field verify the actuator goes to full closed when commanded closed, and verify it goes nearly full open when commanded open. Again, full open really not is a problem. Full close is critical for valves due to seat erosion and for dampers and energy control. So if you have a steam valve, and the higher the pressure, the more critical this gets. If that valve goes full close but actually stays open at 0.5%, it will destroy the valve. The steam will actually erode the seat in a very short period of time. So you need to make sure that the valves go full close. The way you do that is the adjustment linkage on the top of the valve actually adjusts how far down that stem goes to close off the valve. So you need to get that, make sure that's adjusted correctly so it goes full close. If it then it limits the stroke and it only goes 99% open, you're good, not a big problem. Even if it's a globe valve, you will still get full flow, but you need to be full closed for sure. How can you tell if it's full closed? Well, number one is you can listen to it, you can hear it, especially if you carry a field stethoscope with you, which I do, and you just listen to it, and if you hear flow through the valve, it's leaking by. You gotta solve that. Other instances you can tell that it's flowing by, but that's a sure one if you can hear it. If the actuator does not go fully closed, adjust the linkage so it will go fully closed, and that's easy linkage fix. And it'll probably affect how much it goes open, but it doesn't matter. Dampers and valve flow changes, very little flow between 90 and 100%. Very little effect. It's all down at the closed end. Here's a control point-to-point test sheet, and we've gone over these test sheets already in the other session. Test form is tested by controller again. Test for point calibration and ranging on the same form. This is the controller data. This means what it kind of controller it is. Is the network completed? Is it up and running? Here's the I/O points on the system. This is the binary point test data. It's here, yes, on, open, closed, yes, no. This is the analog point test data. So here's where we test what the system says, what the control graphic says, and what the offset is. And then over here is the verification. We actually put an offset in the machine to do that. And a verified signature and notes. So here we record the actual offsets, and what needs to be recorded in this form becomes a part of the report. But one piece of information that needs to get to the operators is what offset do we actually put in the controller. And this is something that needs to become obvious in your report. And the reason is because if this controller fails and they replace it, the offset goes out the window with it. So they need to know what offset they had to put it back in, or recalibrate the sensor anyway. That'd be a better way to do that. So this point-to-point testing, we've gone over in 2 different modules now, so hopefully that was easy. It is beneficial to do. It's actually easy to do, just takes some time. So I hope you enjoyed this video. Appreciate you being a subscribing member. Appreciate you watching the videos. Thank you very much. Have a great day, and I'll catch you on the next one. Thanks.